In this video, we'll take up the concept of mutual inductance. If you have a coil sitting here with a current I1, that current in the first coil can set up a magnetic field, and the magnetic field produces a magnetic flux. The magnetic flux from that coil may in fact intersect a second coil. If the current is changing in the first coil, then the magnetic flux that it produces is also changing with respect to time. And that changing magnetic flux that's intersected by the second coil can induce an EMF in the second coil. So here you see we have some red field lines. They shouldn't be crossing there, but my drawing's not too good. And they cross, and some of the flux, not all of it, but some of it, goes through the second coil. This flux lines going through the second coil will be changing if the current in the first coil is changing, and that will induce an EMF, which I've listed over here as V2, or maybe E2 if you prefer, since it's really not a voltage but an induced EMF. Now this is similar to what we had for self-inductance, except here the current that causes the flux is in a separate coil from the induced EMF that it produces. So what we're going to do is define inductance in the same way we did with self-inductance. M, standing for mutual inductance, is defined to be the magnetic flux linkage in the second coil divided by the current that causes that flux. Now the flux leakage depends on the number of turns in the second coil, N2, times the flux going through that coil. And we'll choose the notation that this is V21. 2 stands for in coil 2, and 1 stands for caused by coil 1. And we'll divide that by the current that causes it, and the current that causes it is the current I1. So in self-inductance, we use the symbol L, and we had only the N for the single coil. We had the flux, and that flux was in the coil itself, and we divided by the current in the coil. Here, the current is in a different coil, the coil that causes the flux linkage in the second coil. To show you that, I'm now going to put on a video. In this demonstration, we've connected a primary coil to a sine wave generator and a secondary coil just to an ammeter. We will now adjust the frequency and amplitude and watch what happens to the induced current in the second coil. Lowering the frequency. Raising the frequency. Lowering the amplitude. Raising the amplitude of the signal in the primary coil. Notice the secondary coil gets all its energy from the primary coil by mutual inductance. We'll now adjust the distance of the secondary coil to the primary coil and watch what happens to the induced current. Moving the coil back and forth changes the amount of flux, of magnetic flux going through the secondary coil, and therefore the mutual inductance. Adjusting the orientation changes the amount of magnetic flux. This is the essence of mutual inductance. We now saw a problem involving mutual inductance. Consider two coils. The first coil, it has a length L and an area A, and it has a set of turns, and the number of turns that it has is N1. So N1 turns, and it has a length here, let's say we'll call that L. Now the magnetic field for this infinitely long solenoid is mu naught times the number of turns N sub 1 times the current flowing through it I1 divided by the length L. This produces a magnetic flux. That flux is equal to B times A, which is equal to mu naught N1 I1 over L times A. Now, there's a second coil that is set exactly over the first coil. This coil has exactly the same length, and all the flux that went through the first coil is now going through the second coil. And the second coil has the same length, L. So we have this flux created by the first coil going here, but now we have N2 terms in this second coil. To calculate the EMF here, the flux linkage, we have N2 times phi, which gives us mu naught N2 N1 I1 A over L. We now divide the flux linkage by the current that caused this thing to find the mutual inductance. So it's N2 phi, and the current that caused the flux was I1. So we get mu naught N2 N1 I1A over the length times I1. And we can cancel the current I1, and we get a value that depends only on the geometry of the problem. Mu naught N2, number of turns in the first coil, the area divided by the length. Now you can also rewrite this if you prefer. It's mu naught little n1, little n2 times the area times the length. And if you look at that, that's exactly what we got earlier in self-inductance, except there we only had one coil, so we had the number of turns squared. Here we have the number of turns per length in the first coil times the number of turns per length in the second coil. So we get a very similar result. This is the essence of mutual inductance.